Modern theoretical physics and continuum mechanics rely heavily on modeling infinity as an asymptotic, unreachable limit. When these systems are pushed to extreme scales and a continuous mathematical function strikes a hard topological boundary, standard calculus typically suffers from quantization failure and information loss. Forcing discrete integer logic into a continuous topological manifold generates severe geometric resistance. Advanced topology defines this precise tension as Nash-Moser topological friction, a state where the smoothness of a function literally shreds under the pressure of rigid constraints. The theory of infinity, or TOI, offers a rigorous ontological correction to this dynamic. It proposes that reality and mathematical structure are not built upward from nothing, but are instead carved downward from an infinite continuum using exact topological boundaries. This carving process is governed by the generative triad. The triad defines a formal operational sequence. It maps the raw state space, applies relational symmetries to dictate shape, and finally imposes an origin evolution to lock down what survives in the physical cosmos. This diagram shows precise celestial spheres and exact geometric ray intersections acting as bounding constraints. It reflects Johannes Kepler's historical mandate to replace perfect classical assumptions with strict, constrained geometric limits. Within the TOI framework, catastrophic computational failures at these boundaries are never discarded as observational errors. They act as deliberate modality shifts. At exactly these limits, a mathematical space sheds its continuous surface to reveal the unbreakable discrete structures hidden beneath. Book 74 of the Formal Canon investigates this exact mechanism through a rigorous boundary audit. The goal is to observe exactly how a continuous mathematical function survives a collision with a hard topological boundary without shattering into computational chaos. The test initiates with a highly specific starting geometry, an asymmetric semi-quartic Fibonacci ellipse. This construct is mathematically locked to the discrete Fibonacci constants alpha and beta, which serve to harmonically constrain the system. This diagram displays the semi-quartic Fibonacci ellipse and its underlying equation. The structure contains a profound mathematical imbalance. While the y-axis maintains a sweeping parabolic degree 2 curvature, the x-axis is elevated to a rigid degree 4 profile. This mismatch in geometric degree creates a dangerous structural instability known as spinorial tension. The curve generates a severe spatial gradient, creating mismatched trajectories aimed directly at the central origin. The immediate operational objective of the audit is to locate the exact perimeter intersection where this imbalanced manifold strikes the horizontal x-axis, evaluating the limits of its geometric resilience. Forcing a geometrically asymmetric object into a hard, continuous, discrete boundary initiates a catastrophic structural crisis. To accommodate the immense stress, the manifold must either surrender its underlying symmetry or elevate its dimensions entirely. To evaluate the manifold's limits, standard algebraic procedure requires isolating the x variable. This allows us to map the right and left continuous branches of the curve along the grid. Here is the isolated root equation for the positive branch. The constants alpha and beta are trapped inside a fourth root operator. We impose a boundary condition, setting y to 0, striking the rigid threshold known as the shadow plane. Calculating this intersection over the real continuous plane creates an immediate algebraic paradox. The syntax demands that a strictly positive principal fourth root must somehow yield a net negative sum. Standard computer algebra systems instantly recognize this impossibility. They return an empty set, forcefully halting the simulation and classifying the shape as a computational dud. The TOI framework interprets this halt entirely differently, identifying this event as the principal root sieve. This is an impassable syntactic safety wall, hard-coded into algorithmic solvers to prevent the violation of fundamental algebraic integer laws. The physical universe prioritizes strict real number containment over complex plane continuation. By refusing to compute an impossibility, the sieve forces the observer to abandon the positive branch and seek a valid structural resolution elsewhere. The boundary evaluation shifts to the negative branch of the isolated equation, seeking an alternate mathematical contour capable of bypassing the principal root sieve. Applying the y=0 boundary condition to this left-hand branch yields a structurally sound result. The syntax equates a positive scalar to a principal fourth root, satisfying all algebraic constraints and making the evaluation legally computable. Auditing the actual polynomial fed into the solver reveals massive algebraic bloat, including the sudden, unprompted appearance of y to the fourth power. This spontaneous generation of degree 4 variables constitutes a severe dimensional violation of the original parabolic starting geometry. The evaluation system received no explicit algorithmic instruction to mutate the variables. The sheer internal pressure of hitting the strict boundary evaluation forced the mathematical system to elevate its own structure. The manifold initiated a stealth upgrade. To survive the boundary and resolve its dangerous asymmetric spinorial tension, it spontaneously generated a higher topological symmetry. To prove the exact nature of this structural mutation, the framework employs apophatic decompilation. This is a rigorous mathematical technique used to strip away the continuous, multiplied noise of massive integers, revealing the pristine, discrete structural invariants hiding underneath. The decompression sequence expands the binomial using the coefficients of Pascal's triangle, 1, -4, 6, -4, 1. The massive polynomial systematically reduces, collapsing the chaotic asymmetry cleanly into a perfectly symmetrical degree 4 Lemay curve. In Cartesian geometry, this specific degree 4 superellipse is mathematically defined as the Fibonacci Squircle. It is a highly constrained entity that exists strictly halfway between a perfect square and a continuous circle. Under pressure, the continuous manifold shed its weak parabolic curvature. It adopted the extreme topological rigidity and sharp corners of the squircle, utilizing the higher degree as massive geometric ballast against the impending stress. With the geometry officially upgraded, the system proceeds to mandate the final boundary test. It enforces the condition y=0 upon the newly symmetric Fibonacci squircle. The squircle's leftmost boundary is separated from the y-axis by an impassable expanse of empty coordinate space. This structural deficit causes surjective invariance failure. Because the evaluation map cannot cover the target space, its mod 2 degree is forced to 0. Failing to achieve compact closure physically pushes the entire mathematical system into a non-compact state, leaking into infinity. This precise threshold is classified as a not-infinity event. It is an active mathematical primitive that demands a forced modality shift to prevent total topological collapse. This shows the mechanical threshold triggering the not-infinity failure. Calculating the final coordinate requires extracting the fourth root of a massive negative number. Traditional real number models crash at this undefined operation. The TOI ontology dictates strict adherence to the law of topological mass exchange. This law mandates that unsealable geometric tension cannot simply be discarded as an observational error. Instead, the total system mass must be meticulously conserved by violently shifting the data into an orthogonal spatial geometry. To execute this shift, the system invokes the fundamental theorem of algebra. The theorem mathematically guarantees that any non-constant polynomial of degree n possesses exactly n roots in the complex plane. Euler's formula is applied to transform the unresolvable negative real number amberpolar coordinates. Euler's formula expresses complex numbers using exponential functions, allowing the system to legally calculate roots by rotating the negative value through a complex phase angle. This shows the spatial distribution of the ejection. Extracting a fourth root generates exactly 4 distinct coordinate points, separated evenly by intervals of pi/2 radians. The mass is extracted from the real domain and cleanly sequestered into complex phase space. Under extreme pressure, the continuous manifold reaches its absolute limit. It sheds its continuous camouflage, compresses, and rapidly bursts outward into 4 fixed discrete points. This Spinorial Fracture, the hypersquare ejection, demonstrates a fundamental mechanical truth. The universe resolves infinite boundary collisions not through computational failure, but through the absolute, unbreakable conservation of Platonic symmetry.